All right, so that then tells us that we were ready to begin today's discussion, which is the topic of conjugation. Now, conjugation, I'm sure you're comfortable with. If I give you a complex number, you know how to conjugate it. Right? Whatever is the imaginary part, you replace j with minus j, and therefore you will get the complex conjugate. So we go through the steps of conjugation, except that we go through it very, very carefully, very systematically, and we get the conjugation relationships that are available to us. Okay. So x of z is equal to definition of a z transform, summation n equal to minus infinity to infinity x of n z power minus n. Now, if I conjugate x, that means I'm conjugating the entire left hand side, which means I must conjugate the entire right hand side. What are the complex, possibly complex values? X could be complex, z is complex, so therefore x has to be conjugated, z has to be conjugated. So we get x conjugate of n, z power minus n conjugate. Now we look at it a little bit more closely. If you write z is equal to r e power j omega, z conjugate will be r e power minus j omega. Z power minus n is r power minus n e power minus j omega n. I am looking at the red portion. Z power minus n conjugate will be r power minus n e power j omega n. The minus j omega n becomes j omega n. By the same token, z conjugate is e power minus j omega. Z conjugate raised to the power minus n will be r power minus n e power j omega n. So what we are concluding from this step is z power minus n conjugate is the same as, is identically equal to z conjugate raised to the power minus n. So we can write this as summation n equal to minus infinity to infinity x conjugate of n, z power minus n conjugate, we are going to write it as z conjugate raised to the power minus n, whatever from this particular expression. Okay, now I'm going to do the last step, which is very important. I'm going to take x conjugate and replace z with z conjugate. Replace z with z conjugate. Okay, wherever there is z, replace z conjugate. So a complex number, you take its conjugate and conjugate a second time, you get back the original number. Z conjugate will be z. So therefore, this particular summation is n equal to minus infinity to infinity x conjugate of n z power minus n. Very, very important, this expression. Okay, so what it tells us is that if I have x of n with a z transform which is x of z, then x conjugate of n, the conjugated sequence, is going to have a z transform that is given by x conjugate z conjugate. And suppose that this had a ROC Rx, the question is what is the ROC of the x conjugate n? Okay, first point to observe, if x of n is a right-sided sequence, what will x conjugate of n be? Also a right-sided sequence. You just taken the conjugate of each of the terms. If it's a left-sided sequence, the original sequence, so whatever is the original Rx, this will be of the same type. It will be, if it's right-sided, it will remain right-sided. So let us take a closer look at what happened to the poles and zeros. That's going to be important. So let us assume a rational form x of z, product of numerator terms 1 minus ck z inverse divided by product of m 1 minus dm z inverse. Okay, so now I want to look at x conjugate z of z conjugate. X conjugate of z conjugate, numerator k 1 minus ck conjugate, z is conjugated twice, so what you get is z inverse again, and the denominator is pi over m, product of m terms 1 minus dm conjugate z inverse, dm conjugate z inverse. Okay. So where are the poles? the original sequence, original Z transform had got poles at dm, Z equal to dm, where m equal to 1 all the way through up to m. Now x conjugate of Z conjugate has poles at Z equal to dm conjugate, where m equal to 1 all the way up through m. Now very, very important, in all these cases, do a quick sketch of the pole 0 plot. Okay. Now supposing we had the pole at a location, some Z0. Okay, so let me just quickly sketch this. A pole, so marked with a X, that is the pole location. So the pole has a radius, let's call that as R1, and an angle omega 1. Okay. Conjugate means you make the angle negative, minus omega 1, but radius remains the same. So the conjugate location is going to be at an angle minus omega 1, and the pole will be at exactly the same location. Okay, basically same radius. So this is, and similarly, if you had a pole outside the unit circle. Okay, let us say that this was the pole, it was at a radius R2 and an angle omega 2. Okay, the conjugate pole will be at the same radius, but it will be at a negative angle. Okay, minus omega 2, conjugate. Minus omega 2. So I want you to now be able to visualize the poles and the conjugate location. Now what happens if the pole was on the real axis? Okay, on the real axis, conjugate means same. So basically the conjugate is at the same location as the original pole. So you will either get a conjugate location, same radius, negative angle, or if it's a real pole, then real valued pole, then it will be at the same location. Now in all cases, we are looking at the region of convergence with regards to the pole radius R2. So basically one circle that you will have to look at with regards to R2 and another circle with regards to R1, right? So those are the poles that we are looking at. And so whether it is the original pole or the conjugate pole, the radius has not changed. So therefore the ROC has not changed because it is still a right-sided sequence, and therefore the conjugate sequence has got a Z transform that is given by X conjugate Z conjugate, and it has the same location in terms of the poles, right? In terms of the ROC, same ROC, because the radius of the pole is the same. Okay. Now there is a couple of properties that are derived from this, which you can easily verify. So basically we have just now looked at the property number 5, which is the conjugation property. Conjugation property, okay, which says that if x of n has got a Z transform given by x of z and an ROC Rx, x conjugate of n will have a Z transform that is given by x conjugate Z conjugate with the same region of convergence R of x. Okay, now property number 6 and 7 are straightforward. Once we have this, I would just like you to verify. Property number 6 says the real part of x of n, which is 1/2 of x of n plus x conjugate of n. Okay, this has a Z transform that is given by 1/2 of x of z, again by inspection we are writing it down, plus x conjugate of z conjugate. Two terms, ROC of the first one is R of x, the second one is R of x. So therefore, the region of convergence for this particular, for the real part of x of n will be R of x. Okay, property number 7. Number 7, imaginary part of x of n. Okay, please verify. This is something that I would like you to look at and write down. This will be equal to, this will have a z transform. Z transform given by 1/2 of x, or 1 by 2j, sorry, 1 by 2j, x of z minus x conjugate of z conjugate, and the R region of convergence is Rx. Okay, now comes a very, very important Z transform property, which is called time reversal. And we will show you in a minute why time reversal is an important characteristic that we are very interested to study, and why we are interested to look at it extremely carefully. Okay, so let us take a look at the property, and then we will look at the discussion. Okay, so if you have x of z given by summation n equal to minus infinity to infinity x of n z power minus n. Okay, now replace m with minus n, okay, or minus m with n, either way. So then what you have here is summation m equal to minus infinity to infinity x of minus m z power m. No change, just a change of variable, that is what we have done. Okay, and the next step is extremely important. X of 1 by z, z is replaced by 1 by z. What will you get? You will get summation m equal to minus infinity to infinity x of minus m z power minus m, because it will become 1 by z power m, which is z power minus m. This basically means that the time reverse sequence x of minus n, okay, x of n has got a z transform x of z. The time reverse sequence has got a transform which is given by x of 1 by z. Z has been replaced by 1 by z. Okay, and just like we did in the in the previous property, let us write down what the implications of this are. Okay, there is a numerator set which is over k 1 minus ck z inverse divided by product over m 1 minus dm z inverse. Okay, now x of 1 by z, I want to know what are the poles and zeros of this z transform, right? So it will be product over k 1 minus ck z divided by product over m terms 1 minus dm z. Okay, so for x of 1 by z, I get the poles at the following locations. The poles are at z equal to 1 over dm, where m equal to 1 through uppercase n. Okay, the pole locations have gone to the reciprocal position. What was a dk for the original? So this one had a pole, this one had poles at z equal to dm, m equal to 1 through n. The time reverse sequence has got poles in the reciprocal locations. Okay, and it's very important for us to visualize what is happening with the reciprocal locations as well. Okay, so if this is the unit circle, I'm going to use a very similar example as previous one. I have a pole which is located at this radius r1 with an angle omega 1. Okay, reciprocal 1 by so this can be written in this case d1 is equal to r1 e power j omega 1. 1 by d1 will be equal to 1 by r1 e power minus j omega 1. Okay, so where is the reciprocal pole? It is at the negative angle. The angle is minus omega 1. The reciprocal is 1 by r1. So the previous one was inside the unit circle, now it will be outside the unit circle. This has got a radius 1 by r1. Okay, so you can see that it goes to the reciprocal in terms of radius, conjugate in terms of the angle. That is the reciprocal position. Now on the other hand, if I have a pole outside the unit circle, so I have it at this position, the corresponding reciprocal will be inside the unit circle but at the conjugate angle. Okay, so I want you to visualize that this is the location of the reciprocal and if you have a if it so happens that you have a 0 on the real axis, a pole on the real axis, it will be the reciprocal. The reciprocal, if the original pole was inside the unit circle, now you will have it outside. Outside means inside. So basically you will get, these are the ways in which you have to visualize the reciprocal locations. Okay, now why are we taking so much effort to look at the locations? It is for the following reason. Supposing the ROC of x of z, the original sequence was given as mod z greater than RR less than RL. Okay, supposing that was what was given to us. Okay, now extremely important that we are now going to look at the ROC. We want to look at or get to know what is the ROC x of 1 by z, right? That's the, so how do you do that? You say 1 by z is now the new variable. It is between the same two limits RR less than RL. Okay, but what is the condition on z? Take each of these individually, you will get 1 mod of 1 by z less than RL. This will give you the condition mod z greater than 1 over RL. Similarly, if you combine the condition that RR is less than 1 over mod z, this will give you the condition that mod z is less than 1 over RR. Okay. So what is the new region of convergence? The new region of convergence is going to be mod z less than, it is less than 1 over RR and greater than 1 over RL. Now I would like you to just sort of, we have written down the expression. Does it make sense? Does it seem reasonable what we have written down? Okay. Previously, you had a pole inside the unit circle, R1. So the region of convergence, if you wanted to look at it as the right-sided sequence, what will it be? Mod z greater than R1. Okay. Now, when you do the reciprocal, the pole has gone outside the unit circle. And so now if you want to do the region of convergence, it will be a left-sided sequence where mod z is less than 1 over R1. So whatever was the limit of your right-sided sequences now becomes, the reciprocal of that becomes your limit of your left-sided sequences. So basically the right-sided sequences and the left-sided sequences, because the poles interchange locations, now become reciprocals and are the reverse position. So mod z is limited by, to the right for left-sided sequences, 1 over RR. And for the right-sided sequences, it is given by mod z greater than 1 over RL. So this is a very, very important element for us to capture, and therefore I want you to keep this relationship in mind, derive it, make sure you are comfortable with it, and we will look at some examples which will utilize this particular result. Now, let us go on to deriving property number 8 in our sequence. Property number 8. The property number 8 says, look at x of z. X of z equal to summation n equal to minus infinity to infinity x of n z power minus n. We know the following. This has a region of convergence which is given by r subscript x, okay, or we can think of it as mod z greater than r less than rl, left-sided sequences, right-sided sequences. Okay. Now we know that x conjugate of z conjugate, this is the sequence, this is the z transform of the sequence x conjugate of n equal to minus infinity to infinity x conjugate of n z power minus n with the same region of convergence Rx. Okay. Now I am going to do these replacement just like we did before. M is equal to minus n, so this can be written as m equal to minus infinity to infinity x conjugate of minus m z power m, x conjugate of z conjugate, just a change of variable on the right hand side, has not affected anything. Now the last step is extremely important. I am going to replace z with 1 over z, so which means x conjugate, I am going to replace 1, so it will be 1 over z conjugate, okay, very important. What is this equal to? Right hand side, summation m equal to minus infinity to infinity x conjugate of minus m z minus m. Okay, so basically I replace z with minus z, so therefore I got z power m became z power minus m. So what this tells me is that x conjugate of minus m, that is the conjugated time reverse sequence, x conjugate of minus m has got a z transform that is given by x conjugate 1 by z conjugate. Okay, extremely important. Now what I would like you to do is go back and look at the transfer function of x of z. Okay, so this will be product of k 1 minus ck z inverse divided by product over m 1 minus dk z inverse. Okay, remember what we did for the conjugation. So one more step, x conjugate of 1 by z conjugate. What you will get is product of over k terms 1 minus ck conjugate z. Okay, it will be ck's will get conjugated, z will get conjugated twice, and 1 over z will be replaced by 1 over z. So you will get this as the expression divided by product over m 1 minus, this should be dm, 1 minus dm conjugate z. Okay, where are the poles? The poles are at z equal to 1 over dm conjugate, where m is equal to 1 all the way through m. Okay. Now, if the reciprocal was at reciprocal radius and the negative angle, okay, what is 1 over d1 conjugate? This will be 1 over r1 e power j omega 1. So which means the reciprocal conjugate is sitting on the same angle as the original pole, but at a reciprocal location. Okay, so basically it's at the same radius as this one. So this is at 1 over r e power j omega 1. So here is the important thing to look at and understand. So draw the following unit circle. Okay, I'm going to draw this line, this line. If this corresponds to a pole Z1, okay, this is 1 over Z1. This location is 1 over Z1 conjugate. Okay, and finally this is Z1 conjugate. I want you to visualize original pole, conjugate, reciprocal. Where does the reciprocal go? It goes in the negative conjugated angle, and reciprocal conjugate comes in the same angle. So I want you to visualize all of these things very, very carefully. Okay. Now if the pole was on the real axis, conjugate will lie exactly on itself. So 1 over Z2 and Z2 conjugate are in the same location. Z2 comma Z2 conjugate are in the same location. This is 1 over Z1, 1 over Z2 and 1 over Z2 conjugate are in the same location. 1 over Z2, 1 over Z2 conjugate, if it is on the real axis. But if it is on the anywhere in the complex plane, you will see that these are the relationships. So let me look at one more time. X conjugate of minus n has got a Z transform which is given by X conjugate 1 by Z conjugate. Okay, and if the original ROC was mod Z greater than RR less than RL, remember when you do the reciprocal, the two will interchange, right? Zeros inside the unit circle go outside, outside comes inside the unit circle. So please verify that in this case it will be mod Z greater than 1 over RL, just like when you did the reciprocal conjugate will be the same as reciprocal. This will be 1 over RR. Okay, very, very important that you get this visualization of what happens when you do time reversal, what happens when you do conjugation, and what happens when you do time reversal and conjugation. Okay, and maybe it's a good idea for you to write down all the different all the different relationships in a way that you have the clear picture. So for example, if you have x of n, the Z transform x of z, mod z greater than RR less than RL, X conjugate of n will give you a Z transform X conjugate of Z conjugate. The ROC did not change because you only the poles moved to the conjugate location. RR less than RL. X of minus n, the time reversal. This resulted in X of 1 by Z. The region of convergence got flipped around and reciprocal, so it is greater than 1 over RL, less than 1 over RR. And finally, when you look at X conjugate of minus n, then what you get is X conjugate of 1 over Z conjugate where mod Z is greater than 1 over RL, 1 over RR. Okay, whenever there is a time reversal, you find that the location of the poles will interchange inside the unit circle to outside the unit circle. Conjugation does not affect the ROC, but reciprocal will affect the ROC, because now your region of convergence will be completely different.